Thank you very much. Can you hear me? Yeah? Okay. Yeah, it's a pleasure to be here. Thank you for coming. It's an incredible crowd. So it's an honor for me to have the opportunity to talk today. I would like to spend some time about talking about high performance and scalability for data analytics. We all know that in the past, Moore's law has serviced us quite well, right? So we, for more or less for free, every 1 to 2 years, we got double the complexity in our transistor, so we get more and more power in our compute resources. However, there is one trend that is actually outpacing the compute power, and that is data. So the amount of data that we produce every day is growing faster than the compute power that we can add in our processors. So that is, of course, becoming a problem for people who are trying to analyze the data. So data analysts and machine learning engineers and all that. So if you get more and more data and your processor is just not fast enough and doesn't, is basically the compute performance is not getting as fast as the data is growing, we have a problem. Here are just some numbers, what we expect next year. So this is next year, not in 10 years. It's next year, the amount of data that will be produced every day. For example, an average internet user will produce 1.5 gigabyte of data per day. If you just look back maybe 10 years, it was fast to press a CD and send it to your photo printer to get your photos printed. Because that was faster if you just drove it by car there than trying to if it's just 10 or 20 pictures, it was just too slow. But next year we will have 1.5 gigabyte per day per user. And if you go to the other hand, traffic, of course, is something that will produce a lot of data. But on the other far end, of course, is the cloud video providers. So they will almost have 1 exabyte of data per day. So this is really, really huge. Now, if you're a data scientist and you want to analyze this data, you usually start with exploring the data, right? And now try to explore, let's say, 5 terabytes of data in one day, and then you have to come up with your model and do all the training and the prediction and all that. It's almost, today, it's basically impossible because it's just too much data. So what people usually do is, because they can't process all the input data for the training, what they do is they just take a subsample. So just a subset of the data, create the model, do the data exploration, create the model, and do something. In most cases, I'm not a statistician, but in most cases, that's probably fine enough. But in some cases, if you have very sensitive data, like for healthcare or whatever, you cannot be sure that you're not missing something that is really, really crucial for your data. So something is needed to make that more performant. So you need more performance, more scalability to actually process that data, because you want to, of course, add as much data in your exploration phase as you can. And the scalability here is interesting because a single compute unit just is not fast enough. So you have to add more and more compute units at the same time. So that's the kind of scalability we are talking about here. Most of these data analysis tasks are actually handled in Python. And that is more or less adding fuel to the fire. So it's making things worse, because Python is not actually known to be a super fast language. It's actually known to be super slow, right? Python is a very nice language. It's super easy to use. It's super productive, but performance really sucks. It's really bad. So if you, for example, compare it, you write a code, let's say you're a skilled programmer in C, you write it in C, right? You have a good compiler. You might even know how to use threading libraries like TBB or OpenMP. And if you write the same code now in Python, you lose a performance between 50x or 5,000x, and sometimes even more. So the discrepancy is really huge. And there are 2 factors why the performance is so bad in Python. One is the interpreter, right? Python is an interpreted language. So the interpreter reads one line, transforms it into some intermediate format, and says, okay, this is what I need to do, then executes the native code, goes back to the next line, etc. So it's a really intensive process that happens. So if you have, we had a nice example today where it just showed 2 + 2. So that was the Python command. But if you see what happened behind the scenes, it's really huge compared to it's just a single operation on the CPU. If you do it right in a lower level language. The other problem is the GIL. the global interpreter log. So it's as bad as it sounds. It's a log. It's a mutex that the interpreter grabs whenever it executes Python code. So for every instruction in Python that it executes, it gets one log, and there's only one log for all the interpreter, executes that, and releases the log. And then when it executes the next instruction, it gets the log, executes Python, releases the log. So there's no parallelism in the Python interpreter. So we're talking about CPython, which is 95% of all Python usages. It's really bad. So there's no way you can really do good parallelism in Python. And I'm stressing this because parallelism is actually the most limiting factor for performance in Python. So you might guess that the interpreter is already limiting your performance quite a lot, but it's actually not that much compared to the parallelism that it's hiding. So we made an experiment. We used the stock option pricing algorithm called Black-Scholes. We implemented that in Python, so very straightforward implementation. Implemented the same thing in C, so no tricks, no nothing, just exactly one-to-one translation into C. Used a compiler with no vectorization, no parallelism, and then we let the Ninja programmer and said, okay, please make it as fast as you can. Those are the three numbers that you see here. The Python code yielded into 1/3 of a million operations per second. So we measure how many operations, how many options it can process per second. So it was 0.36 million operations per second. By just applying a C compiler with no parallelism or anything, the speed up was 55x. This, I say only, it's only 55x, right? It's significant, of course, but if you look what you gain when you add parallelism like vectorization and threading, which is an additional 350x. So it's 7 times more, in this case, it was 7 times more important to get the parallelism right than just removing the interpreter, right? And this was just for a single machine, so one processor. So if you really need to scale out because your data is too much, of course, you're adding another dimension, because if you go to distributed memory, of course, you have to do some more stuff because, messages and all that needs to be done. Luckily, there are some approaches to get that done, in particular in the data science space for data analytics. So the two most popular ones are probably Spark, which is unfortunately not Python. So if you're trying to use Spark in Python, you have several additional problems because it's its own universe and you have to go back and forth between the JVM. And the other is Dask. Dask is becoming more and more popular. And what we ideally want to achieve is the optimal trade-off between performance, which is here on the y-axis, and productivity on the x-axis. So we know Python is super productive, so it's on the far right-hand side. And MPI, for example, for message passing, for doing distributed computation, is known to be, let's say, the best performing technology they can use. But it's hard to use. So it's on the left, but it's very high in performance. But in Python, it's on the right, but very low in performance. So where we actually want to go with a solution for Python that lets you distribute and parallelize is where the green box is. High performance and high productivity. And unfortunately, the tools that are being common today, like Dask and Spark, they have chosen an implementation route that is not ideal in two terms. One is the productivity, because they're using lazy evaluation. So lazy evaluation is very elegant and it's nice, and in many cases it's probably sufficient. It's okay, but sometimes you run into trouble because it just behaves unexpectedly. So if you have to be aware of this lazy evaluation. So it's not like in Python, you're really changing, you have something new. And sometimes it's very confusing what's happening. And on the other dimension, it's the performance. They have chosen let's say, the hype of going into a tasking system. So they're translating communication patterns into a task tree, and then trying to emulate the communication patterns like all reduces broadcasts with task graphs. That's an implementation choice. So they decided to implement a master executor model. And as we see here, this is not really ideal So what happens is, let's say you have, this is just a hypothetical program, and you have, let's say 2 or 3 instructions where you need to do communication between the tasks. So what these systems do is, they, from one instruction, like a, let's say a group by or a join, they create a task graph. The master creates a task graph saying, okay, those are the dependencies between the small, tiny tasks that are to be executed for a join. Distribute that to the processes, they do their work, and then they communicate back. So you have all this back, fan out, fan in, fan out, fan in, of these waves of tiny tasks. And what makes it even worse in these implementations is that they do lazy evaluation. So they don't, if they would compile this statically, it would only be half as bad. But now they do it even lazily. So whenever, if that's in a loop, whenever they execute it, they have to create the task graph, do all this fan out and fan in at the same time. So but they're basically doubling the problem by doing it lazy and tiny tasks. So there is actually no reason why Spark or DAS should actually not implement it more efficiently. So I'm not trying to say they're no good or anything. I'm just saying there are limits to the solution that they decided to implement DAS and Spark in. And later in my talk, I will show you like an alternative approach that we have chosen that actually gets rid of these limitations. Fundamentally, our belief is that if you want to get performance and scalability out of Python, what you need to do is you just need 2 ingredients. One is performance libraries. So you probably know that Python has a very nice way, or not nice, but has a very efficient way of going down to C. So you can easily plug in a C library into Python, and if you are in C, you can release the GIL, and then you can explore and use all the parallelism in your hardware. So by going down to C with performance libraries, you can actually get super performance even in Python. So you're hiding the implementation in a different language. So that's basically circumventing the GIL, but it works very nicely. So this is the performance libraries. By using those, you can already get very good performance. But the other is, the other secret or the other ingredient for getting good performance is compilation. Sounds a little strange because Python is an interpreted language, but Anaconda came up with a just-in-time compiler called Number that works on a function level, so you can actually compile a function level for a given type signature and then run it natively. So it will get rid of the interpreter entirely. So once the cheat compiler has compiled your function for a given type signature once, the second time you call it, it will directly go to native code, which means if you combine performance libraries written in C or C++ and the Number compiler, you actually can get very, very close to Ninja level code written in C or C++. And I will show some examples where we actually have done that. Here's just this is basically give an example how this could look like. So here's some code that shows you how Number works. It's very, very nice. It's keeping the productivity of Python. So it's not inventing anything new, like you have to have a pre-execution step, like in the traditional where we have to first run the C compiler, get a binary, and run the binary. It's all within the Python environment. And it's done by using the decorator. So you just decorate your function, say, please cheat this function. And when you execute that function, when the function is called, the cheat compiler will just chime in, compile it down to native, and execute it. The next time you call the function with the same types, it will see, oh, I already compiled it, so it can directly go to the native code. So so the productivity is really, really the same as before. It's just a decorator. It's super easy to use. Well, in theory, of course. If you go to the details and want to do super ninja stuff, there are, of course, several options and configurations that you can do to make it even better. For example, of course, the trick for compiling down to native is always the typing. So the typing is a little sensitive, but in many, many cases, like if you use NumPy arrays or standard data types, it's actually very easy. The other side is the performance libraries. So what I think I mentioned most of this. So because from Python you can easily go down to C, you can implement things like NumPy, for example. NumPy is a very good example. It has high-performant implementations for array computations, for linear algebra or something, but all of that is actually implemented in C. But you use it from Python, and going down to that, it has all the parallelization and all that in it. It's very, very fast. In our, Intel has some even lower level implementations of certain performance libraries, like the math kernel library, MKL, or TBB, or DAL, and I will talk a little more about that later. And we're trying to plug those libraries into standard Python packages to make them faster. One thing that I want to mention about this library is that with a given library, like the MKL or the Intel DAL, it automatically it's future safe in the sense that on the interface, you don't care what hardware you actually run, right? If you buy a new computer, you run the same code without any recompilation, and it will automatically go the fastest route, because we, as Intel, provide you with a highly optimized library that already has all the code paths necessary for the new hardware that might come out. Coming back to Black-Scholes, so you see here a list of operations that are actually needed to implement a Black-Scholes algorithm. So there are some array operations like array multiplication. There's a log, an exponential function, inverse square root, and things. And this diagram here compares, it's like super microkernels, comparing the Python call to NumPy with a direct call to MKL, so the fastest native speed you can ever get. And the percentage of this native performance. You see in all cases, the NumPy code that you get with the Intel NumPy is very close to native. So it's usually around 90%, so it's always larger than 80%. So it's almost the same as native code, even though you're using actually NumPy. And on the right-hand side, you see what's happening if you write this in NumPy, in Python, and then apply number. And so you, as I said, you combine these two ingredients, the just-in-time compiler and the performance libraries, and in the end, the performance is 87% of native. So rather than having a slowdown of 6,000 or 60,000 or whatever that was, we're now very, very close to native performance. And we actually didn't really change the code. We just added a decorator, right? Internally, under the hood, we use the performance library, and then we use the decorator to compile that function. All these performance, so we have a distribution, so it's called the interdistribution. The sound is a little weird. Is that okay? Yeah. Okay. So we have something called the Intel distribution for Python. It's something that you can download, or we have also channels online on anaconda.org. And we provide like performance critical packages. So if you do some data analytics, you use NumPy or SciPy or scikit-learn or whatever, those are basically compiled and packaged in a way that they are optimized for performance. So we plug MKL under the hood or other performance libraries, and you can just get them. So it's for free, so we don't charge anything here. But it's all pre-built. Most of this you could do on your own by compiling it yourself with the right flags, etc. But we get frequent report that is not that easy. And I can confirm from time to time that is pretty involved to get that right. So here's a huge list of things that's in our distribution. And just look it up on the internet and you can Google for it. So there's a lot content in it. And most of this, of course, is focused on something where you need really compute power. So if you are like a Django user, for example, it's probably not what you're looking for. But if you're doing like real math heavy and computation heavy, this is something you should definitely look out for. Let's get a little more specific for data analytics. You saw the title. It says performance and scalability for data analytics. So what a typical data analytics pipeline looks like is you have an exploration phase, right? So you get the data somewhere, you have the data input, then you do data pre-processing, and then you apply some kind of machine learning. You create your model, and then you have sometimes you do prediction. And for these, and we tend to divide these into, let's say, two phases. One is the exploration phase, and the other is the machine learning phase. And for both phases, they are like standard packages that most people use. For exploration phase, people use Pandas. Pandas is the de facto standard, and with data frames and all that, and a nice operation, it's very easy to use. There are also, of course, other technologies. I mentioned Spark before, but if you're a Python user, if you really want to use it, it's probably fine if you stay within PySpark. But as soon as you want to combine it with other Python packages, it's becoming dangerous, because then you have to copy data back and forth, and if you're dealing with a very large amount of data, that's of course a problem. One of our technologies that's basically driven by Intel is called HPAT, High Performance Analytics Toolkit, which is the alternative to Spark that I will describe in detail later. On the machine learning side, the de facto standard is scikit-learn. It's a package that provides all kinds of machine learning algorithms. It's very, very popular. Similar to Pandas, we are providing optimizations to the scikit-learn directly. So people don't change their code, they just use scikit-learn, and it's get much faster because they use our scikit-learn, or the way that we assemble scikit-learn. But of course, you could also use Spark, same caveats as before. Or you use DAL for Pi, which is an Intel library. And I will talk about that later as well. Actually, I'll start with this right now. So DAL is the acronym for Data Analytics Acceleration Library. It's an Intel library that is optimized for machine learning. So it's like the math kernel library, like the MKL, but on a slightly higher level and specialized for data analytics. So it's not enough to just use the BLAS library like MKL to make that really fast, because there are additional optimization that we can apply, like doing the right blocking, doing the right threading, getting the caching right and all that, so that the things like k-means or logistic regression really perform well. And what we have done is we have basically put this DAL library underneath scikit-learn. So scikit-learn, you will still use scikit-learn with a non-scikit-learn API, but under the hood, DAL will actually be the engine for scikit-learn, make things much, much faster. Here are some examples of algorithms that we have iterated in scikit-learn. And again, we are comparing against native performance. We define native performance as the performance that you would get if you use DAL directly. And we don't know any library that is faster than DAL for these algorithms. So you can treat this as the gold standard for performance, for example, for k-means and the other algorithms that you see here. And again, with one exception, the performance is always 80% of native code or faster for the Intel distribution, which is the dark blue one. If you use the stock Python, so the pip installed scikit-learn, the performance is so bad that you can barely see it. So it's much, much, much slower. Just to give you an impression, here we are comparing the stock k-means initialization. So there are different initialization methods for k-means, so finding the initial centroids. Just comparing the performance of the stock scikit-learn with a scikit-learn that's optimized by DAL from Intel, and the performance is more than 20x faster than that thing. So the performance that's left on the table with a standard implementation is tremendous. So you can really get a huge performance benefit. It's very easy to use it. So you just install the DAL for Pi, and the DAL for Pi brings patches that you just need to enable. So if you have a scikit-learn already on your system, you install DAL for Pi, and then you can either on the command line with a -m monkey patch all the scikit-learn algorithms that are supported right now, or you can case by case enable the monkey patching programmatically if that's what you want. The very important thing here is that we are passing the scikit-learn test suite. So numerically, you can assume that our optimized scikit-learn behaves identical to the stock scikit-learn. So this is actually was the most trickiest thing to do, so that we actually achieve the similar result as scikit-learn. So there are other implementations from other vendors that have a similar interface to scikit-learn, but we are the only ones that actually pass the compatibility test suite. In DAL for Pi, or DAL itself, provides a huge set of algorithms that you might need for machine learning. I'm not going to cover all of them or any of them. I just wanted to briefly show you that there's a whole set of algorithms that you can use. So you don't need to use scikit-learn. You can also use DAL for Pi directly. DAL for Pi is the Python interface through the DAL library. And all these algorithms are actually available. For example, and here, linear regression, naive Bayes, decision forest, and all this is available. But here, we actually, if you want to use these, which are not iterated in scikit-learn itself, you have to use the DAL for Pi interface. This is not the same as scikit-learn, it's only scikit-learn similar. Right? It's very similar in spirit, but we have chosen here and there some other design. We have made a few other design choices. Here's an example how, so for people who know scikit-learn, this might look, this should look very familiar, but it's slightly different. So if you want to do a k-means, for example, with DAL for Pi, first of all, of course, you have to import DAL for Pi. Then let's say we just read a CSV file. And what you have to do in k-means is actually you have to call two algorithms because finding the initial centroids is a different task than finding the actual k-means clustering. So we first create an algorithm and configure it with certain parameters. For example, the 10 means we want to have 10 clusters in our k-means, and then the method should be ++. Then we compute, and the return is our centroids, so the initial centroids for the k-means clustering, and then we call the actual k-means algorithm with a compute. So one major difference to scikit-learn is that in our API, we are trying to separate the concerns a little more strictly. So instead of having one huge behemoth of an algorithm where the fit, the transform, the input data, the output data, the results, and all that is in one big thing, we are separating things into results, algorithms, and input data. But that's probably the biggest difference that we have. And we, of course, then, because we separate the fit and the transform and the prediction, you don't call .fit, for example, you call compute, because it's a training algorithm. This is what it looks like if you are on a single node. But one of the biggest benefits of DAL for Pi is actually that you can run it on a cluster. And you can run it on a cluster with known best-in-class technologies, which is MPI. So under the hood, we're using MPI. So the user of DAL for Pi doesn't see any of the MPI. So you use DAL for Pi as before, but you can actually scale it out to a cluster, and the scalability is almost linear. And the user doesn't really have to care about all this communication, all this business here. And how this works, just because I was talking a little about the bad decision here, about the tiny waves of dynamic tasks. On the right-hand side is actually how this works with MPI. So instead of having a master that creates these waves of tasks and sending it out and in, we have long-living processes. And each process executes the same program. So each process knows exactly what it needs to do. So when data needs to be exchanged, we can minimize the amount of data that needs to be exchanged to the absolute minimum. For example, if you only need nearest neighbor communication, all you do is exchange a message to your neighbor left and right, and that's it. Or if you need a global communication like a reduction or an all-to-all, we can actually use decades of research in this space, which all went into MPI and have an optimal communication pattern, which is not possible if you go a route like this one. And here is how this code would look like if you run it on a cluster. You see there's almost no difference. The yellow parts are the ones where the difference is. First of all, you have each process needs to know each portion of the data. In this case, we decided to say, okay, each process reads its own CSV file. So this is the first line with the yellow stuff. So each process basically reads its own file. And then we do the same thing as before. The only difference is when we configure the algorithm, we say, please run this as a distributed algorithm. We just say distributed equals true, and that's it. That's all the change, and we will run to a cluster up to as many nodes as you want, because we're using MPI under the hood. So, and then if you want to execute your program, the only thing, of course, you have to start all the processes, and we just use MPI again. Instead of saying Python.your Python script, you say MPI run -n, how many processes you want, your Python script. That's the only difference, so it's really straightforward, very easy to use, and super scalable. So we made some scalability measurements here. with k-means and linear regression. You see two bars for each of the algorithms, the orange bar and the yellow bar. The orange bar is the so-called strong scaling, which means we fix the data input size and just double the amount of resources, so double the amount of nodes in our cluster. Then, of course, whenever we double the number of clusters, the performance should halve, right? So that's why the orange number is going down. So it's almost linear. So that's the strong scaling. And that's the same for linear regression and for k-means. And the weak scaling is the yellow bar, which stays flat, which means when we double the amount of compute resources, we also double the input size, which means the performance should, of course, stay flat, right? And that's what you see here, the performance stays flat. So we have 32 nodes in the larger scale, and each node has, and that sums up to 1,200 cores. So it's not super large, but it's already quite sizable. And you see it almost has no performance degradation. And just to put that in perspective, what that means for performance, if we look at the linear regression, on a 32 node cluster, the input size for the largest thing here, in the hard scaling, in the weak scaling was 2 terabytes of data. So we did a linear regression on 2 terabytes of data, and that just cost us 1 second and a bit. Right, 2 terabytes of data in 1 second and something. Or if we stayed with a small input size, it was almost 70 gigabytes in just 50 milliseconds. So it's really super fast. So you can really process huge amount of data in almost no time. The other one thing that, where Dask is really good is this notion of computing out of core. So you have like a huge input data set, but it doesn't fit into memory, but you still can use Dask to process all the data. It will not be super fast, but it will at least work because it loads the data when it needs it. We call this streaming. So DAO4Pi supports streaming as well. So if you don't have the data at once, you don't want to load it, it doesn't fit into your memory, you can use the streaming mode. So you basically provide one block of data after the other, so one by one. And it's similar to the distributed mode. It's almost no change in your code. It's just, you say streaming equals true instead of distributed equals true. And of course here, I just basically assume that we have a generator called read next, and it just returns you the next block of input data. And when you're done with all the input data, you just say finalize because you're done with all the computation. So this also works. So that was on the machine learning side of things. Just remember this pipeline. So we had the machine learning side on the right-hand side. So we have a solution for single node performance and for scaling out to a cluster, which is easy to use and highly scalable. Now, what do we do on the right-hand side? No, it's on the left-hand side. What do we do on the left-hand side for the data preprocessing? The only thing that we know of is Dask, Spark. But as I said, I don't believe it's really that great in scalability. So what we provide is, so we're working on some things. It's still in incubation, so it's not a full product yet, but we have many prototypes with customers and it's really working well. It's HPAT. But before we come to this, we also do the same for Pandas as we do for scikit-learn and NumPy. We try to optimize the existing packages. So we write patches for scikit-learn or for Pandas or for whatever and upstream that. And so whenever someone compiles his own NumPy or whatever, he can actually build the packages with our optimizations. And we have done a similar thing for Pandas for the CSV read. So for some reason, the CSV read was super slow in Pandas. So we applied 2 patches and then compared the performance. We made 3 measurements. One is, actually all of them apply some optimization because this is the speed up over the stock Pandas, right? So we applied the HPAT, the compilation technology that I will talk about later. The Pandas optimizations that we put in for the pull request that you see up here, and then the combined here. You see, just by applying our patches, we got 80 times speed up in CSV reads. The HPAT optimization, so if you use HPAT on that, is not as much, but the nice thing is those optimizations are orthogonal. So if you combine them, you actually get a speed up of 500, depending on the platform you're running it on. Now, let's go to this magical HPAT, the High Performance Analytics Toolkit. It's a compile technology, actually. So it's building on top of number. So it's also working on a function level. So you decorate your function with a HPAT JIT instead of number JIT. And then what it does, it analyzes your function and does some distributed analysis. So it knows how to handle Pandas code, for example. It knows how Pandas can be distributed and parallelized. So it knows all this data parallelism and all that stuff. So it does this automatically for you. There's nothing you have to do. It compiles it down to a binary and creates an efficient MPI binary. Again, we're going to the SPMV process way of doing things. So running the process and using MPI for high efficient communication patterns. So you decorate your function with HPAT JIT, and what you get is a highly efficient MPI binary. So no more interpretation, no tiny tasks, no nothing. Everything is super efficient. I've prepared some examples to show you what's actually happening. So because it sounds a little like this is the holy grail of automatic parallelization, of course that's not the case. So we have not invented the automatic tool that can parallelize and distribute everything on Earth, right? The data analytics space, in particular Pandas, is very narrow. So the kind of stuff that you can do with Pandas is well known, it's well understood. And the communication patterns for that are not that difficult in most cases. So we know exactly what to do. So you can't apply this technology to an arbitrary HPC for code, for example, because what the HPC folks do is much more complicated. So you can't do this for arbitrary code. But for Pandas code, for example, it's very simple. Of course, when you have your data analytics code, you have to start from scratch, right? So where you read in the data. So if you don't parallelize the data input, you're basically lost, because you can assume that reading in the data is a large fraction of your time that you spend in your pipeline. So what HPAT can do, it can also parallelize the data input. As an example here, we use a Parquet file. So what happens is the black one is your file. It's one block of file, one monolithic file. And what HPAT does, it knows, okay, in this example, for example, we have 4 processes. So it splits the file into 4 blocks, and each process reads just its chunk. So the blue one reads the first quarter, and the yellow one reads the last quarter of the file. So when it's done with a Parquet file reading, each process holds just a quarter of the entire file. And all of this is done automatically. So you don't write any of this here. This is all what HPAT does for you, because you annotated it with hpat.jit, right? So this means that reading the data goes in parallel. So if your file system supports this, or if you have a parallel file system, for example, this will give you a 4 times speed up. Of course, this makes the assumption that your file system can actually cope with parallel access. Now, let's go to the next level, and let's do some Pandas operations that are data parallel. So many of the things in Pandas are trivially parallelizable because they're just data parallel, like filters, for example. Here in this example, we just say, okay, let's filter out from this data set all the rows where the power is not 0. Right? It's a data parallel per row. We just filter out some rows. But we can also do data parallelism by modifying columns, for example. Here we say, okay, we just multiply the hour column by time 2. And all this can go in parallel. You see here again, this is just visualizing how it works. So we have this monolithic sequential file. We divide it into four blocks. We read it in parallel, and from then on, everything is parallel. There's no data communication needed because it's just embarrassingly parallel. We can filter out the rows. Each process can do it on its own. It doesn't need any communication and any information from neighbors. And the same is true for the multiplication in a column, because there's no communication, no information needed between rows or between columns. And again, HPAT can all do this automatically. You don't need to do anything like this. Now, of course, some of the operations in Pandas are more complicated. For example, a reduction. Something like computing the average, the means, something like this. There, of course, the communication is a little more complicated. So just take this as a placeholder. This is not actually the communication that's happening. It's just a placeholder to show you that even more complicated things can be handled by HPAT. So you just do your regular Pandas code, and HPAT will create something that works like this. So we have this parallel input. Then each process produces some local partial result, some intermediate result. It does some communication, and when it's done, all the processes have the result of the reduction. A reduction means that the result is much, much smaller in size. That's why we can replicate the result of a reduction on all the processes. The next level of complexity, if you do a group by. Group by is already a relatively complex operation, and to do that in parallel on a distributed system is quite tricky. So doing this manually is really a lot of work. But luckily we have HPAT, so it knows how to do this. Again, parallel input, local results, partial results, some communication, and finally you have a distributed the distributed outcome of your group by. If you do a group by, it's only usually meaningful if you do a reduction, but that reduction is not a single thing, it's like a vector of results, and that's why we can distribute the result of a group by. Right? In comparison to a normal simple reduction, we have a distributed result here, because we have, of course, much more output. Again, like with Dart4Pi, if you want to run it on a cluster, you have to use MPI run instead of just running Python. And then all that will just happen magically behind the scenes. You have no need to know how NPI works, and all that is hidden from you. This is just another example to show you what all kinds of things you can already do with HPAT. One thing that is super important here to note is that we can process strings and timestamps. So Pandas is notoriously bad in performance when it comes to handling strings and timestamps. And if you combine all these features, you can get like astronomical speedups, and we'll show some examples later. This is the scope of what HPAT can currently do. So I won't go through all the details, but it's a very large scope. So Pandas is a huge, 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 super wide interface. Right? So we can't support everything. So we're focusing on the stuff that is really important and most people use. Yeah. If you're interested, it's open source on GitHub. You can always use it. We also have binaries that you can just download. So conda install HPAT, and that's it. But I don't want to. I need to mention one thing, because it's a compile technology. Of course, there are downsides to it, because when you compile, the only way to do an efficient compilation is if you have enough information about the types. So your code, the function needs to be type stable. Pythonists might not really know what that means, because types, no one really cares about types in Python. But what it means is that for a given type signature, any variable that you create in your function must not depend on the value. Here are some examples where the type of a variable actually depends on a value. It can be a function that depends on a value that's in the middle, or a variable. You say you have a flag, so you inspect the value of the flag. And in one case, it's an integer, and in the other one, it's a vector. So this is not possible, because that way you cannot statically compile, because you can't determine the types. We hope and we think that this kind of code is very rare in data analytics. Of course, if you use it, we can't compile it, but in basically all cases, there are ways to work around it and to refactor your code so they can actually use the compilation. So last but not least, some performance numbers. Unfortunately, I can't show you the codes because it's customer confidential, but we have four examples here where we made some measurements, what the speed up is that you can get with HPAT. So we don't compare against something like Spark or Dask, but you can believe me, it's the difference is huge. So HPAT is much, 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 much more efficient, more scalable than competitive things. But here you see the scalability. So on the left-hand side, you see a financial code. You see, okay, when we run it on, oh, this is just a single machine. It's just a single machine, but it has 56 cores. So we use MPI. We use MPI even on a single core. This is one of the one of the design choices, but because we're using Python, that's very nice because we don't have to deal with the GIL. We work around the GIL by just starting in several processes. So we get a 35x speed up on the full machine using HPAT. The second example is very interesting because we use the window, sliding windows. This is something, for example, if you want to use Spark, it's very difficult to do in Spark. It doesn't work well because of the fact that it's trying to create a task graph. So representing this very efficiently in a task graph is difficult. But if you use MPI, you have specialized methods to do this nearest neighbor exchange, so it's very fast. You can really get very good speed ups if you use this. And let's just go to the last one. It's from a telco company. This is one example where we got really ridiculous speed ups, and that's because we were using strings and date times. So going from the standard implementation in Python to using 4 nodes with 224 cores, we got a 14,000x speed up. This is because we can do all these tricks that we can really utilize the hardware. We can vectorize, we can parallelize. We don't have to unpack, unbox, and box all the Python objects and all that. So we get rid of all the Python stuff and be really native. So if you use traditional tools in Python and you don't use HPAT, for example, you're leaving a lot of performance on the table. So there is hope that you can actually get enough performance and scalability in Python so you can get performance and scalability without sacrificing your productivity that you love in Python. Those are the two tools that basically we provide. So those are really Intel technologies, but they're not closed, they are open source. So just go to GitHub and download them, use them. If you don't want to compile them, we also provide binary packages in our channels. That's what I had.
We have time for questions. Is there any question? No one? Is there one? Sorry, I didn't see you.
Hi, thanks for the nice talk. I am not really familiar with MPI, so maybe my question is stupid due to my ignorance, but how is resiliency handled in this framework? You know, like with Spark, it's a core tenant that's the RDD, it's a resilient and distribute data set. So I'm wondering how does it handle failures of nodes and retries and stuff like this?
That's a very good question. So resilience or fault tolerance is something that is currently not implemented. And I think you probably heard that. MPI is notoriously bad with that. So there is no way to really do good fault tolerance in MPI. You can do certain things, but it's very difficult to implement because if one process in your MPI, if one process goes down, the entire network dies. So we used MPI just because it's a shortcut. So we could use other even lower level technologies to go there. On a higher level, the tiny task and the way that Spark actually solves it with creating all this. So, sorry, let me start again. So one argument that the Spark authors make why the tiny tasks are so beneficial is fault tolerance. And they say, okay, when you control what's happening on a very fine granular level, you can easily say, okay, we restart again, we just have to redo a certain thing. But if you go into theory, what you actually want to do, this is far too fine-grained. So the overhead that you pay for these fine-grained things is It's just super costly. So what we would do, if that's going to be of interest, we would do a checkpointing on a causa level. So we can, like say, like task groups or something on a very low cost grain level, we could do the checkpointing. So we have like prototypes and show that it works, but it's not implemented yet. So we would do a checkpoint restart. But actually, that's a good, can I just make a, is anyone here in the room who thinks that this fault tolerance is actually crucial?
Oh.
1? 2? Okay, thank you.
One question here. Extremely nice talk, extremely interesting. Since Intel is a commercial company, adopting or embracing these kind of things would incur in licenses or at what stage you get licenses? Because you said the two things are open source. MKL, last time I checked, was not open source. So is it completely open source, or at some stage when you use it to a certain level, you need to get licenses for using this?
So except MKL, all the tools that we're using are open source. But I think your question is probably whether it's free, whether you have to pay a license fee or something. So even MKL is free of license, so you can use it for free. So you will never have to pay anything. So everything that we contribute here for Python, all the pipelines are free forever. So you just, it's like GPL, it's not like GPL, but you get a license by using it, but you don't have to pay anything for it. So MKL is the only tool that is not open source, but it's still free. So you don't have to pay for it.
Any other question? We have time for another question. Actually, I have one. There's one? Oh, yeah.
Just one curious, thank you for the good talk. So in the end, it's just compilation, right? Could this, in theory, be compiled also for other CPUs other than Intel CPUs? Or is there a lock on it?
In theory, yes. So Number, for example, and they're actually investing quite a lot to also make the Number stuff work on GPUs, for example. So there's a lot of work going into the GPU stuff. We don't guarantee that it works on anything else than Intel. But conceptually, actually, I don't see any issue with working to at least make the compiler work on any other platform. But of course, it's work you need to do.
Okay.
Any other question? Now, these columns are quite complicated. Question?
Do you need the Intel version of MPI or some other distribution like OpenMPI would also work with DAL?
Yeah, certainly you can use any MPI version that you like. So of course, when you compile it, you have to make sure you're using a binary compatible MPI. And I think OpenMPI is probably not compatible with binary compatible. If you compile it yourself, just use any MPI you want.
Any other question? Actually, I have one. I was wondering if there's any restriction on the hardware. You have to use it. I mean, there's a specific family of processors, of CPUs you have to use to embed this kind of technology, or
no?
No
No,
restrictions.
so basically the whole Intel family of CPUs can be used. And whatever comes out in the future, we will definitely also support.
Of course, I guess. All right, so if there's no other question, thank you very much again for the speaker. Great talk.
Thank you.